All right, guys, good afternoon. We're gonna start with today's class. It's 6:03. Um, as I said yesterday, we're gonna continue with examples on projectile motion in two directions. I have a problem on the screen in which you are being described a situation. So sometimes problems they will describe you or they will provide you with a situation in which you have to sketch it and then of course solve the problem. All right. Now the descriptions are normally quite easy to follow and they give you the information without any extra information that you may not need. Like one complaint that I know students have in math is that word problems sometimes they give you a whole bunch of information or they go on a tangent, right? At least here in physics, um, problems like this they will go to that point, right? So in here you have a situation like a daily situation where you are throwing a ball from a window, right? From certain height. They give you the initial velocity, the angle. The only thing that you have to be careful is that now the angle is below the horizontal, right? And they give you time. That's actually good for this type of problems. When they give you time, they're giving you quite some information that you can use to work, which is why they give you several parts. So you have A, B, C, D, E. Okay. So let's solve this situation by first drawing it. Okay. I think I have everybody. So pretty much what you have in a situation is on the board, right? You have a building with height y naught or y0, and you are throwing the ball in that direction. So that's important, right? Now we have the direction of the ball, not like this, but like this, right? So we have 8 meters per second, and it's still gonna go like this, right? Mind you are doing like, you're throwing something like that. But now the velocity is at an angle. So you still have two components. And the main thing about this example is that the vertical component of the velocity is non-zero, right? The initial. There is a vertical and there is a horizontal. Now, if we go back to the example, they are telling you that the base of the building is the origin. So here, that's the origin. Why do they tell you that? They tell you that because they want you to find the initial coordinates of the ball. So if that's the origin, and this is x, the x-axis, and this is the y-axis, you want to find the coordinates of this point. So because that's the origin, the x coordinate of this point is 0. So you could say that here you are in the 0, comma, y naught. So you just have to find y naught. You have to find the height of the building. All right? That's for part A.
Professor, could you move the camera up a bit? I just can't see what you have written at the top.
Yeah. Yeah. Now you can see it. So you have to find y naught. Okay? That's why I say that it's good that you're given the time. Because you can use this equation. By the way, Uh, Now, because that's the origin, right? You are basically looking for why not. So you could just say, you could just reduce the equation to like this. That. Okay, so let's clarify the signs again. All right. In the problem, they are telling you that the speed or velocity is 8, positive 8. So in real life, right, it's not very common to talk about negative velocities or even negative distances, right, or negative displacement, right? We talk about distance, time, speed, or velocity, and they are always positive because we always think in terms of the value, the magnitude. So the height of the building has to be positive. And since that's the origin, why not has to be positive? Because upward means positive. So that's going to be positive. Now, V initial is V initial on Y. T is time, which is 3 seconds. G is gravity, T is time. So what about here? So since now we're talking about values or magnitudes, we have to think what's going on with the ball as it's going down. As it's going down, due to gravity, the ball is accelerating. So it's speeding up. So we use the positive here. Again, because we are using magnitude values, like the value of the velocity and the value of the acceleration. The value of the acceleration, so now the absolute value of the acceleration is just 9.8. Okay, so you take the absolute value. All right, so I can use this equation. B initial, okay, so what's the initial on Y? That's 8, but that's slanted, an angle of 20. So I can break the velocity into components. 8 cosine 20, 8 sine 20. 8 sine 20, that's V initial on Y. And I'm going to leave it as positive. All right? So now let's solve for the why not. And let's actually use this 20 sine plus 8. 2.73. Okay, so this is 2.74 meters per second. All right, so 2.74 times 3.1, by the way, plus 1/2, 9.8 times 9, 3 squared. All right, so that's how you find the height of the building. All right, or why not, which is the initial coordinates of the ball. So 2.74 times 3. This is 8.21 plus 9.8 times 9 divided by 2, 44.1. So 52.3 meters. There you are. Okay. And these are the coordinates of the ball are 0,52.3 meters. Okay.
Professor, for the y equals, right, you have 2.74. Oh, okay, never mind. I didn't see how I was multiplying, my bad.
Oh, yeah, it's 2.74 times 3 plus 1 half g t squared. All right. There's more though. Now, some of the questions are repetitive. Like, for example, the last question is asking you to find the height. Okay. The height is that. Part B is asking you to find, using right as positive and up as positive, find the x and y components of the initial velocity. So that's Vx, that's Vy. Right? So here, the x and y components of the initial velocity. So this is part A. Part B, they ask you to find Vx and Vy. So now they're asking you to also add the direction signs. Okay. So A cosine is Vx. And because it's towards the right, it's positive. Dy is A sine. But because Vy is going down, for the velocity, we have to add a negative.
Professor, would it be possible to shift the camera up just a little bit?
You went out so far.
Okay.
Perfect. Thank you so much.
So this one we found already. This one was 2.74, so negative 2.74. All right. And A cosine 20 is just going to be bigger than that because of the angle. 7.52. So towards the right, negative because it's going down. Okay. So that is part A, part B. Part C, find the equations of x and y. Okay, so that one, they ask you to find the equations for x. For y, we have an equation already here. So we just have to solve for x. Basically, was an equation to find the range. So to find the range, we have to use Vx. So we found y already. Now let's find x. X is Vx times time. Because we know the velocity horizontal is constant, that will be 7.52 times 3. Okay, so
Wait, is it 3 seconds or 9 seconds?
3 seconds. The time is 3 seconds. And if I do that, that's 22.6. That's 23 around it. 23 meters. So we found X, we found Y naught, which is the answer for part E, by the way. Well, let's see what part D. Well, part C and part D. Part C is asking you to find this, just to write this. Okay. And part D is to find that. So what's the horizontal distance? What's the range? That's part D. So C, D. Sometimes, as I said, sometimes these problems, they are kind of redundant in what they ask you. They are taking you step by step. And then part E, what's the height of the building? Well, the height of the building is Y naught, which was 52.3 meters. That's an example of 2 dimensions. Very easy to start. Okay, very easy to start today's class. I think as long as you remember that you have to break the velocity to components, and if you're given the time, it makes things much easier. You just have to use the y equation, which, by the way, that's what I'm going to be doing now. Let's explore more about the parabola sort of trajectory, okay? We've done problems where you have to find the height, the range, the velocity, right? But there can be more, or no more complex, but there can be situations where you want to understand the trajectory of the mass or the object, all right? So let's show you the following. In fact, since it's in the book, let's see. That. I think it's here. There it is, this one. So I want to show you guys this sort of exercise. That. So the X and Y coordinates of a projectile launched from the floor, from the origin, are this. They're asking you to find an equation for the path of the projectile. Okay, so why is that important? Because there are some problems where that equation will be very useful. All right? It's going to allow you to explore other situations like basketball launching situations, or even like I'm going to show you with a water hose. All right? Because at the end of the day, you do have a parabolic sort of situation. So, all right. There. That's V, that's the angle theta. And if I draw the trajectory of this mass, this is what I get. And I already show you that, or you've seen it already, that there is a peak and a line of symmetry. So there is a parabola. And if that's the origin, then this is x, this is the y-axis. So you know from math that you can find the equation of this parabola. That's the objective of that problem I show you. So what is the equation of this parabola? Okay. So I have x v cosine theta times time. That's the x. It's as a function of time. It changes like that. Also as a function of the angle. But the angle is just there. And then y is your y initial, which can be 0. In that case, will be 0. But let's leave it like that. Plus v initial on y times time minus 1/2 gt squared. Okay, so why am I going to use the minus in this case? And this is going to help you. Yes, this is going to help you for your lab that you did yesterday. You see, this is a parabola open down. The parabola opens down. So this is an open down parabola. That means that the quadratic coefficient, remember I was telling you that yesterday, right? This is the quadratic coefficient. So if you do a fitting, it can be like this or it can be like this. The quadratic coefficient is always half of gravity. So if you are using polynomial fitting order 2 or grade 2, which is a parabola, the quadratic coefficient, the absolute value if it's negative, will give you the double of it, will give you the magnitude of the acceleration. So that's why I'm going to keep it negative, because look, right? The linear coefficient is the initial speed vertically. But we know that v initial on y is v sine theta. I have this. So let's find an equation for the parabola. If I want to find an equation for the parabola, my general equation for parabola is y equals to ax squared plus bx plus c. So I have to write the equation of y as a function of x. And I can do that. How? V initial on y is this. But time is as a function of x. I can write time as x over v cosine theta. Yeah. So I can substitute that in here and in here. And v initial on y is this. And let's see what we get. And then I'm going to do an example where we use that. So y is y initial plus v initial on y is v sine theta multiplied by time. But time is this, x over v cosine theta minus 1/2 gravity time squared x over v cosine theta squared. All right. So y will be y initial. Here, if I do the algebra, v cancels with v. Sine over cosine is tangent, right? So I have plus x tangent of theta minus 1/2 gravity, look what we get, x squared over v squared cosine square of theta. So here, that's the equation for this parabola. So C will be y naught. If you launch from the ground, y naught is just 0. If you are on the ground. All right. X tangent of theta. So B, that's your linear coefficient. And your quadratic coefficient, though, now is A negative 1/2 G over V squared cosine squared theta. All right. So that's the equation of this. That's the solution for that problem. So the equation of the trajectory of a projectile is that. And trust me, that is going to help you when they don't give you time, for example. If they don't give you time, but they give you the angle and the speed, you can find any vertical position. Okay? And that's the example we're going to do now in here. There's one I saw here, but there's one that is quite interesting. This one here. There. It's a fireman situation. You see that figure there? They give you a fireman 50 meters away from a building, and is launching, is directing a stream of water from the ground at an angle of 30 degrees above the horizontal with a speed of 40 meters per second, an angle of 30 degrees. At what height will the stream of water strike the building? So you have the figure there, right? The situation is not difficult if you use this equation I just showed. Let's be in there. So you have firefighter or fireman. That's the angle there. And then there. And this is the building. A deal like that, so you guys can see it better. I think that works. Let's see how it looks from their perspective. Okay, so 40 meters per second. The distance from where he is to the building, 50 meters. And the angle is of 30 degrees. So they're asking you to find at what height what's the y value at that instance. All right. Okay. So if the water continues, it will be a parabola. Like that. So you are on the ground. This is the ground. So y initial is 0 meters. To find any value of y, I can use that. So I have the angle theta. I have v. What's v? 40 meters per second. I know gravity, magnitude, okay? What about x? Well, for this parabola, for this value of x, that's your value of y. This point is x comma y. That means that x is 50 meters. So now I can find y. I have v, g, theta, x. I can use that. So now let's use it. Y is y initial, which is 0, plus x tangent of theta, 50 tangent of 30, minus 1/2 9.8 times 50 squared divided by b squared cosine square of theta. So that's 40 squared times cosine square of 30. There you are. All right. This. So here, let's just do. This is 28.8 minus. If you do this one, if you do all that math, I got 10.2. So I subtract, I get 18.6. Awesome. So without time, I can still find y. This is a very important equation. It's not in the, it's in the text, well, technically, it's in the textbook. You can actually prove that, but that's basically using the trajectory of the projectile to find any y and x position as a function of v and theta. All right? So that's another situation. I told you guys that we were gonna go over today. There's another one. We're gonna do the basketball now. All right, so like you can also be asked to find v or theta. Right? You can also be asked to find that. So that's why that equation is very useful. All right. Any questions about this particular example?
So wait, where did the 40 come from? Oh, that from the velocity?
That's not enough. Yeah. Okay, so if you're not given time, but you're given the horizontal range, you can use that equation to find the y value. Basically, the vertical position. All right. All right, let's show you the other example I have here. This one here. There. You have a basketball player, 2 meters tall, who is standing 10 meters from the basket, as you can see in the figure there. And he's shooting the ball at an even angle, 40 degrees, with the horizontal. And I mean, it's realistic. You can know how high the basket is. So 3.05 meters. In this question, they're asking you to find the initial speed. So the value of V. So he can make the shot. All right. So let's do the drawing. While you guys are doing that, I'm going to start doing it here. So you have, it's kind of like the one we just did, but now you have initial height. So let's see. So you have the basketball, who is 10 meters from the basket. Right? Ten point zero. And the basket is 3.05. And yeah, you're gonna launch, and you're gonna shoot, and it's gonna do this. Oh, that's 40 degrees. D. I think. Yeah. Again, it's a parabola, right? But now you're given y. You know how high it has to go. You do have this though. And you have this. Now, my parabola, right, it starts from here. So it goes from a given height. That's y initial. This is the x-axis. So this guy is x. We take that as the origin. So that's a general equation, right? Y is this. Y naught will be 2. That's the initial height. X is 10 tangent of 40 minus 1/2, 9.8, 10 squared over, okay, v squared cosine square of 40. So I have everything. I have everything, right? So I just have to use again that equation. It simplifies a lot because again, in this problem, you don't know time. And you know what's also why this is useful? Because the mass is going up and then down. So using this simplifies the whole up and then down situation. The up and down situation is good when you're given like the velocity, when you're given time, or at least more information. For problems like this, where they give you vertical heights, an angle, right? That is more useful, right? Especially again because they don't give you time. And they're asking you specifically for V now. And you have V in that equation there. So let's see. Let's see. So why is this, right? 3.05 is why not 2 meters plus x tangent of 40 minus 1/2 gravity x squared over v squared. You want v, so that's the variable, cosine square of 40. That's what you want to solve. So you want to get numbers here. Well, you have a number here and here. So let's start by subtracting 3.05 minus 2. That is 1.05. That's 10 tangent of 40. So that's 8.39 minus, so let's see, let's simplify that. We have numbers, it's a b squared, so that will be 100 times 90, so 100 times 9.8 divided by 2. So I get 490 over b squared cosine square of 40. All right. This can go to this side, this can go to that side. So I get 490 over b squared cosine square of 40. That's equal to that minus that. That's 7.34. I don't know that. And then now I can erase this. V squared goes up, this goes down. So V squared from the denominator goes up, and you get 490 over 7.34 multiplied by cosine square of 40. I have to take the square root on both sides, so I get my V. All right, so now let's use this. Okay, so 490 over 559 over 7.34, the square root. 10.64. Well, 10.6 meters per second. There you go. Look at that. I found the shooting speed. All right. So, questions about this? I will say that for problems like this, use that strategy. Okay. We have an exam next week, right? Like the first major exam. I would say expect a problem like this. All right. Simple. I mean, when you're not given time, and they're asking you for heights or even this, so you can use the parabola. It will help you a lot. And actually, this can be used for a lot of things, like footballs. If you want to know how much, if they can clear a ramp, you can just use this. All right. So that's how we are gonna finish chapter 3. All right, unless you guys have any questions, I believe I have covered most of the examples that you can find from Cengage and from WebAssign. So now questions about this? I would say be careful with the math. All right. You want to do it by parts like I do it, so you don't make any mistakes towards the end. All right. All right. Now we can start. Oh. For the first exam, if there's gonna be a study guide, I would say that the WebAssign should be your best bet to practice and to prepare for the exam, and also problems that we do in class. Like for example, this, I don't think there is a problem on WebAssign like this. However, Cengage, these problems that I have done today, right, the three of them can be found in the textbook. So if you go, for example, to chapter 3 in the textbook, if you go to the problem section, that's where you find this situation. So you can always take a look at that. Plus the WebAssign problems where you have projectile motion and of course the free fall projectile motion that we did. There is a problem like that. And also the quiz, like you guys have a quiz on Thursday. That should also help you to prepare for next week's exam. All right. So chapter 3 is the end of kinematics, motion, first in one direction and then in two directions, as you've seen. So what's coming now is to study why motion happens, right? The thing about physics is that at the beginning we start by teaching you guys dimensions, units, quantities, vectors, scalars, and then we use some of that to explain motion, velocity, displacement, acceleration, and of course, speed, distance, and then we have one-dimensional motion, free fall, and now we have had this projectile type of motion, right, or motion in two directions. The one that is left that we're going to do later is circular motion, right? At some point, we are going to study the motion of planets around the sun or satellites around the Earth, right? So we will go back to motion for chapter 7, right? But now in chapter 4,